All right, DHBT device and circuit technology for millimeter and sub-millimeter wave power amplifiers. And with that, the floor is yours.
Thank you so much. So can you see my screen now?
Yes, we can see. Perfect.
Perfect. Thank you so much, Steve, for the introduction. My name is Sarah Hamzelvi, and today with my colleague Filippo Ciabattini, I'm going to talk about D-band load pool characterization of indium phosphide, gallium arsenide, and antimonide double heterojunction bipolar transistors with record 38.6% power added efficiency at 170 gigahertz. We are working in millimeter wave electronics at ETH Zurich under the supervision of Professor Colombo Bolognesi. I would like to start my presentation by giving you an overview of what I'm going to talk about today. So I will very quickly talk about the submillimeter wave load pool characterization from Vertigo Technologies and our indium phosphide DHBT technology. In ETH Zurich, we have actually a standard 300 nanometer indium phosphide HBT technology. First, I will talk about the device design and also the 170 GHz load pool characterization. Then Filippo will continue with our new device process, which is the terahertz emitter fin indium phosphide DHBT technology. Then we will conclude the talk in the conclusion. As we actually already know from this session and also the previous day sessions, large signal transistor measurements are one of the essential characterization methods, mostly for validating the accuracy of large signal models, and also to show and demonstrate the ultimate device technology performance. However, most of the reported data on devices on single transistors are actually limited to the frequency range of less than 100 gigahertz, which is mostly due to the limited commercial availability of load pool solutions. And also, more importantly, devices often get destroyed when we do the load pool measurements because they have to withstand very high VSWRs when in a circuit they do not need to withstand this high VSWR. In this presentation, we are going to show the high-frequency load pool characterization of indium phosphide gas antimonide DHBTs, which will be the first D-band power characterization of a terahertz technology, and we will present the record 38.6% power added efficiency from a single transistor in the whole G-band range from any semiconductor technology. So as Osman already talked about the submillimeter wave load pool characterization from Vertigo Technologies, I'm just going to very briefly show the measurement solution that we used here so that we are not going to lose a lot of time on this. So the measurement setup that we used was actually an active open loop vector modulation concept from Vertigo Technologies. It actually consists of VNAs and frequency extenders and a vector modulation unit. It can do power control as parameters, large signal measurements in 50 ohm environment, in load pool, mixed frequency. We actually specifically only use the load pool solution. As Osman also suggested, mentioned, the maximum frequency is actually determined by the millimeter wave extender, so it can be in general up to terahertz frequencies, but the limitation is actually the maximum power, because the maximum power of the system is determined by the hardware, which is actually the output power of the extenders. So if we have actually quite a closer look at the system, the RF signal is actually being generated by the VNA, and then it passes through the vector modulation unit when an RF power, like a signal which the magnitude is actually being controlled, is going to be sent to the source port, and a signal which both the power and the phase are being controlled will be sent to the load port, and then they are going to be up converted by the extender, and the signal that both the phase and the magnitude of it is being controlled at the output is going to create the active load for us. So I'm going to first talk a little bit about the indium phosphide HBT technology in general, and also the indium phosphide HBT at ETH Zurich. As we have seen, to exploit the high frequency or sub-terahertz frequency range, we need technologies that can offer bandwidths greater than 100 gigahertz. Among all of these technologies, if you also like have a look at the right-hand side picture, indium phosphide DHBT technology is actually offering the most favorable trade-off between the speed and voltage handling among all 9 nitride semiconductors. So the best Johnson figure of merit, which is Ft times PVCO, and the best balanced Johnson figure of merit, which is a square root of Ft F max times PVCO. And among all indium phosphide HBT technologies, type 2 indium phosphide gallium arsenide and timonide DHBTs have continued to grow over the years by showing record FT of 813 GHz, a record F max of 1.2 THz in all bipolar transistors. They have been also successfully used in high-speed mixed mode ICs, and they have also shown very attractive power densities up to W band. We attribute all of these very interesting figure of merits to the near ideal DHBT band diagram of gas antimonide devices. So we use a material as gallium arsenide antimonide as the base of our devices, and that actually creates a type 1 band alignment with the indium phosphide emitter. So we use a composite indium phosphide gallium indium phosphide emitter so that it can have a sharp turn on, a very low power dissipation. And also the use of this material as the base will allow us to have a type 2 band alignment with the collector, which actually will result in no electron blocking, and this also helps us to have a high breakdown voltage and good also like acceptable thermal conductivity. Again, the use of pure indium phosphide will also result in no saturation hole injection, which also will be very good for having mixed signal IC devices. The only disadvantage of this technology will be the lower electron mobility of gallium arsenide and timonide material compared to the well-known gallium indium arsenide that requires us to use thinner bases, but it still actually opens the research investigation on using quaternary materials. So all of these advantages will actually help us in having a very high efficiency technology, because we are having a very high gain in higher frequencies, and the ratio of knee voltage with respect to breakdown voltage is actually also quite low, which results in a high power added efficiency. So I will now briefly talk about all the device design research that we have been doing to optimize our devices for the power performance. We believe that for having a device that is optimized for high power applications, we can do it in two different ways. We can either optimize the layout of the device, or we can optimize the epitaxial layers. What I'm going to now focus on will be the layout optimizations, and then Filippo will talk about the epitaxial layer optimization. We have done different type of investigations on the layout optimization, from dimensions of the device, configuring different dimensions, different device configurations, and also multi-finger structures. Our devices are actually being made in a triple metal self-aligned process. Here you can see also a FIB-SEM cross-section of the final fabricated device. We believe that for power performance, the most important dimensions of the device are actually the emitter length and emitter width. And a scaled device which has a low emitter length and also a small emitter width will result in a high frequency performance and also high gain, whereas a large area device with a longer emitter and a wider emitter will actually result in a high power. So this actually imposes a trade-off in device size selection, which actually is shows a good practice for PA design, that they have to use scale devices, single finger scale devices as the gain stages, and also like larger area devices, multi-finger larger area devices as the later power stages. We have also investigated different device configurations from common emitter and common base structures. Here we have simulated using our large signal model the MAG, MSG of each of these topologies, and we have seen that the common base devices actually show a better gain when they are biased at class A. But like we have to actually take into account that these devices, the common base devices, are actually showing they do not show unconditional stability in the whole frequency range that they are showing, like gain greater than 0 gigahertz, 0 dB. So this actually shows that these devices have to be very carefully investigated, especially their input-output instability circles in the Smith chart have to be considered. Also, we have employed some multi-finger structures, both in common emitter and common base configurations, to see if the multi-finger structure is going to help us in having a good power performance or not. In the common emitter structure, we have actually used single base pad electrodes to have uniform input signal distribution. We have used a completely symmetric layout for the whole design that actually results in a superior RF performance, and the mutual heating between each of the emitter fingers are actually controlled by the interfinger spacing. For the common base structure though, we have used double base pad electrodes so that we can minimize the base resistance and inductance to make them a little bit more stable. Still, the whole layout is completely symmetric, which again results in a good RF performance. But because the emitters are actually now here in some kind of a series, they are like actually connected in series, they might suffer from potential phase delay. One more important thing is that when we want to measure the devices for power performance, it's very important that the signal pads or the GaAsSb pads are actually completely matched to 50 ohms so that they do not perturb the load pull results. So the layout design that we have actually used is also exactly matched to 50 ohm. For the multi-finger common emitter devices, we have an equal input signal distribution, and the emitters are directly connected to the ground so that we do not suffer from any emitter degeneration to lose any gain. For the multi-finger common base structure as well, the GaAsSb pads are exactly matched to 50 ohm, although we are suffering from some potential phase delay in the input signal. Again, the bases are directly connected to the ground so that we can reduce the base resistance and base inductance. So with all this, now I will start talking about the characterization, the load pull characterization of these devices that I just showed here. Before talking about the load pull characterization, one important thing is that we have to always look at the IV characteristics of the device. Here you can see the IV characteristic of a common emitter 4-finger device, and you can see that the bias point for class A bias condition is actually completely different from the best RF performance. You can see that it is completely different from both like a VCE point of view and also the current point of view. Another thing that we have to investigate before starting the load pull characterization is the DC safe operating area of the device, which actually shows us the maximum power consumption density of the device, and we have to always make sure that all the active load lines are going to be below the safe operating area of the device. We have also found out that what is the maximum achievable current density so that we can find out the best quiescent point for class A. And as I also showed earlier, the MAG-MSG of common emitter devices shows actually a quite different gain for best FTF max and also class A. So this actually shows that our gain is of course going to be much lower when we are biasing the devices in class A conditions, but actually that will be somehow cancelled out by the fact that we are going to have a high power at these conditions, because we will be having a very high voltage and current swing. So I just wanted to quickly show the load pull measurement procedure that we used in Vertigo Technologies. So we started the load pull measurement by doing actually load pool at one fixed frequency and fixed P-in to find out the P-out or output power and also PAE contours. And after finding out the contours for each of the devices, each frequency, we did another power sweep at the matched load. We actually found out the optimum load and we matched the device to that load to find out what is the -1 dB compression point, what is the saturated output power, and what is the peak PAE of that device. And this whole procedure has actually been done for different P-ins. The good thing about the vertigo technology system was that this whole procedure was actually done in very fast, and compared to the solution that we have in our lab, which is active closed loop measurement at 94 gigahertz, was much faster. Here you can see the measured load pool results at 170 gigahertz of common emitter devices for single finger and multi-finger devices when they are actually being measured at their -1 dB compression point. You can see that as the number of fingers are actually increasing, the gamma optimum is actually also going closer to the edge of the Smith chart, which actually shows that we are going to suffer from a larger matching loss if we use that device in a PA. And one more important thing is that because we were able also to measure the S parameters, measure the power controlled S parameters of the devices with the vertigo technologies, we were seeing that we were unconditionally stable in the entire Smith chart for 170 gigahertz for all these common emitter devices. We also repeated the same measurements for common base configuration and different number of fingers. We again see that by increasing the number of fingers, the place for optimum load is also going closer to the edge of the Smith chart, which actually will be imposing a larger matching loss. But if you see here, all these red places in the Smith chart, they are actually showing the unstable region, and you can see that the instability regions are actually covering a very big part of the Smith chart. So it means that our common bases are in general at 170 gigahertz showing instability, and some instability techniques such as using a capacitor in the base or a resistor in the collector are needed for these devices to be measured without any problem. After finding out the optimum load, we actually measured the power performance of devices for different emitter lenses. You can see that single devices with different emitter lenses actually show a high output power as we increase the length of the device. That was completely expected. But the PAE actually decreases quite dramatically, and that we attributed to the lower transducer gain of a longer device. We also repeated the exact same measurements for different number of fingers. As you can see, we have measured 1 finger, 2 finger, and 10 finger and 4 finger devices for a 10 micron long device. And we again saw that the saturated output power is actually quite high for a 4 finger device, 13.2 dBm, which was also completely expected. And the PAE actually decreased for 4 finger devices, and the best PAE was for a single finger device. The only thing that you can also see in this picture in the left, on the left side, you can see that our 4 finger devices were actually not saturated, and we were not able to drive the 4 finger devices to the saturation, and the reason was the limited input power from the extender. So after this first round of measurements, we actually repeated this whole measurement again at Vertigo Technologies with a new set of extenders that they had a elevated P-in, and they are very new, the extenders from VDI, that we can see now that the output power actually increased from 13.2 to 14.5 dBm, and the power efficiency also increased. So we were actually able to drive the device to saturation a little bit more, although it's not completely saturated. So with this, I would like to stop now and give the floor to Filippo to continue with the epitaxial layer optimization.
Sarah, before Filippo starts, do you want to take a look at the questions from your presentation?
Sure, sure.
So I see I see three. Can you give numbers of max efficiency you see as a function of harmonics above 100 gigahertz?
As a function of harmonics, I cannot really give, but as a function of frequency, we have seen that it almost actually scales with the frequency with 1 over f. So as we go to higher frequencies, the PAE actually decreases with 1 over f scaling.
All right. The second question, did you bias your DHBT device by forcing current or voltage on base? Did the extent of instability region get impacted by choosing to force current or voltage?
So for common emitter devices, we have actually measured them with both of the biasing conditions by forcing current and also voltage, and we saw that for both of them it was actually stable. But for common bases, each of these biasing schemes, like biasing with a forced current or a voltage, was not like really impacting the instability, and the common bases were still unstable. And we saw that like forcing current and voltage was changing the device performance a little bit, but not the stability performance.
All right. And then there's one last question from Wilfredo. Very nice paper. How can I get the PDF copy? And the question, that's one question. The second question is, if increasing more than 4 fingers, there are issues in the optimal load, then what are the negative impacts by using one finger, knowing that one finger has less output power?
So about the first question, I can also share the PDF of the presentation. These results are not yet published, so results from Filippo's part are have been submitted to European Microwave Conference, and my results have been also submitted to MWTL, but we haven't received the acceptance yet. And also about the second question, so by increasing the number of fingers, as actually he has Wilfredo has suggested, we are going to go very close to the edge of the Smith chart, and we will be having like a lot of problem in matching our devices. And then also like a one finger device will really be not completely sufficient for us from a power performance point of view. So I think what we will, because we are also using these devices to design PAs, and for PAs we will probably use 4 finger devices, but still not very large emitters, so that we do not lose a lot of gain, and also we are still maintaining the output power.
Okay, that's all the questions that I see here.
Hey Steve, can I ask one? This is Tushar.
Hey, Tushar.
Hey, I have been listening. Yeah, so I just have one question for maybe Sarah, and maybe Chong can also comment on that. So I have done pretty much a good number of tape outs in InP technology, and just the bare technology FTF max sometimes go to almost around 600 gigahertz. But when you design your transistor, maybe due to the interactions, your FTF max will reduce to say 400-ish. Now, say my fundamental frequency is 90 gigahertz or 100 gigahertz. Typically, these devices are like low voltage and low breakdown devices. And I mean, if I take model, for sure, model will just show some numbers. If I want to play with second harmonic at the load, I will still see efficiency variation as a function of second harmonic load impedance, which can typically go from 6 to 8%. And what typically I have seen that if I try to push my second harmonic load, say in the resistive part near open, then I start seeing like larger voltage swing, or even in class J, you will see reasonable voltage swing, even if your second harmonic is reactive. And in that case, it starts impacting reliability a lot, because the reason is when you're designing, like, say, common emitter stack or common base stack, then you don't have control over harmonics. And a lot of times you will start seeing that reflecting as devices blowing up, or it might be turning up in reliability. So to summarize, what I'm trying to ask here is, do you have had chance to play around and understand more that, does second harmonic really impact efficiency numbers, and also how it impacts the voltage waveform, because that indirectly will also impact the reliability of the device.
Thank you so much for this comment. I'm afraid to say that we have actually not investigated the higher harmonics of our devices. And I cannot really comment on how would that affect the efficiency of a device. If Chong has something that can add, that would be great.
Well, at higher frequency, we're talking about maybe a low frequency. Maybe Osman can give you a bit more insight on this at the low frequency range, but at high frequency range, we haven't explored a second harmonic neither. So unfortunately, I can't answer this question.
No, I mean, I have pretty much done up to 100 gigahertz, but I was just curious to know if somebody has tried out playing with all this waveform engineering somewhere around 110 gigahertz fundamental frequency. Up to 60 gigahertz, I understand this pretty well, and I have seen the impact. So, okay, sounds good. No problem. Thanks.
Thank you, Tushar. Good hearing from you. With that, Filippo, the floor is actually, let me introduce you, and then the floor will be yours.
Thanks.
Filippo Ciabattini. Close?
Ciabattini.
Is a PhD student at Millimeter Wave Electronics Group, ETH Zurich, under the supervision of Professor Colombo Bolognesi. He received his bachelor's in science from the Polytechnic of Turin in Italy in 2017, and his master's of science in nanotechnologies for ICTs, a joint master among Polytechnic of Turin, InP Grenoble in France, and EPFL Switzerland in 2019. His main research area is the process development and characterization of high frequency indium phosphide, gallium arsenide. I still don't know what these. Now the floor is yours.
Yeah. Okay. Can everybody see my screen?
Yes.
That's good. Yeah. So thanks, Steve, for the introduction, and thanks, Sarah, for giving the first part of this talk. I'll try to be as brief as possible. So Sarah so far focused on the layout optimization on indium phosphide gallium arsenide DHBTs in order to extract the maximum P out of our transistors. Instead, I'll show you a different way of extracting the highest possible P out of a single finger HBTs, which is to optimize as best as possible the epitaxial layer. So the motivation of this is pretty straightforward. Heating and thermal degradation are big issues in all 3.5 technologies. The reason is pretty straightforward. Looking at this, if one looks at this table, indium phosphide and the related ternary compound semiconductors have a very poor thermal conductivity if compared to silicon, or even worse, silicon carbide. This, of course, becomes a problem when the transistor, such as HBTs, which are mainly used as power devices, are driven into high power operation because the device heats up and then starts to degrade. This affects the performances, for example, in PAE. PAE changes when the temperature of the device increases. If the temperature increases, the gain of the transistor is supposed to decrease, and the knee voltage is supposed to increase, and overall this leads to a decrease of the power and the efficiency of our device. So we decided to investigate the effect of different emitter and collector designs on the thermal characteristics of our transistors. So we propose you 3 different epitaxial layers. One that we call the standard, which is what Sarah presented so far, which has been the standard epitaxial layer in our group for a number of years. Then a new emitter fin technology, which features a thinner emitter layer. And then third, the emitter fin technology, so thinner emitter with also a thinner subcollector epitaxial layer. Very briefly, the epitaxial structures. So this is the standard epitaxial layer that features 20 nanometers thick gallium arsenide antimonide base. What we call the emitter fin epitaxial layer, as you can see in red are highlighted the epitaxial layers that undergo a change with respect to the standard. So the gallium indium arsenide, the emitter contact layer is shrunk from 35 down to only 10 nanometers, and the heavily doped indium phosphide is shrunk from 130 nanometers to only 20 nanometers. Pros and cons of these epitaxial structures. The major con is the fabrication complexity increases, even though it increases, but also gives us one more degree of freedom, which allows us to, say, change the fabrication a bit. The thermal resistance is reduced as the heat is shunt in a better way through the emitter, because the emitter is the whole transistor is higher. As we gain a high one more degree of freedom in the fabrication, and we can drastically reduce the base resistance of our device. Then the third epitaxial layer features the same emitter, the same base. The collector is slightly different. This indium phosphide subcollector, 50 nanometers, is reduced to only 0. And gallium indium arsenide collector contact layer is shrunk from 20 to only 7.5 nanometers. Here, pros and cons. CBC is intrinsically higher in this transistor, in this epitaxial layer, but the thermal resistance is further reduced. Just a note on how the devices look like. This is a standard device. This is an emitter fin with this funny emitter-looking contact. Main difference is here we have a thicker base metal, and the base separation between the base metal contact and the emitter mesa can be tuned by tuning the width of this fin, and thus we can drastically decrease the base resistance. Then we thermally characterize our transistors with our different epi layers. In black, you see the standard structure. In red, the emitter fin standard, and in blue, the emitter fin with the thin subcollector. On the left side, you see the thermal resistance. On the right side, the junction temperature. As I will mainly focus on the 10 micrometers HBTs. Let's see what happens for the 10 micrometers long HBTs. We have more or less a 30% reduction in thermal resistance and roughly 30% decrease in junction temperature. The decrease in junction temperature is what really allows us to drive our devices to a higher power, to a higher bias, without degrading the performances of the transistor. Then I look at the IV curves. This is the IV curve of the standard epitaxial layer. This is the same IV curve that you saw for the 4-finger common emitter HBT from Sarah. Let's just look at the highest P out bias point. You see it happens around 1.3, 1.4 VCE. But instead, if we look at the emitter fin, let's see at the best FT for both the two epi layers happens around 1.0 VCE. Best F max around 1.1, 1.2 for the emitter fin epitaxial layer, but is pushed all the way to 2.0 volts for the emitter fin with the thinner subcollector. And the highest P out. So this is the bias point where we managed to extract the highest P out of our transistor. As you can see, for the emitter fin, this happens at 1.8 volts, and for the emitter fin with the thinner subcollector happens at 2.0 volts. Just a note on the ref characteristics. You see, this is the FTF max measured at the highest P-out bias point. You see both type of transistor feature Terrace class F max with a very good FT. But we are here to talk about load pool. So let's see our load pool characterization that was carried out in at Vertigo Technologies in Delft in the Netherlands. So in this graph, the black curves are P-out and the red curves are the power added efficiency. Solid curve is 140 gigahertz, dashed curve is 170 gigahertz. So just focusing on the emitter fin, as expected, by increasing VCE, P-out increases at both 140 and 170 gigahertz, and it reaches at 140 pretty good level of 11 dBms, and PAE reaches at 140 gigahertz 39% of power added efficiency. If we look at, sorry, emitter fin with a thinner subcollector, so the best, say that the epitaxial layer that features the lowest thermal resistance, we managed to bias this device and to measure it in load pull up to 2.0 volts of DC. P-out follows almost linearly, increases almost linearly with the collector emitter voltage, reaches at both 140 and 170 gigahertz, above 10.5 dBms of output power, and PAE is above 38% at both frequency points. Here, just a comment on the P-out and PAE contours on this chart. For the emitter fin, at 1.8 volts of VCE, as you can see, at both 140 and 170, they are quite close to the center of the Smith chart, even though, especially at 140, the measurement was not perfect. You see that the contours don't close. But yeah, we were in a rush when we were measuring, unfortunately. But the peak P-out and peak PAE are extremely good, especially at 140 gigahertz. And if we see a emitter fin with a thinner subcollector at both 140 and 170, here the contours close to the center of this Smith chart, and excuse me, and P-out stays above 10.5 dBms at both frequency, and PAE is above 38. Here again, we just report gain and PAE against P-out versus P-out for both epitaxial layer. As you can see, these are basically the same data that I reported in the previous slide, just in a displayed in a different fashion. 140 gigahertz, the emitter fin reaches goes above 11 dBms of output power and above 39%. And the emitter fin with a thinner subcollector at 170 gigahertz reaches 10.7 dBms of output power and is above 38.6, and is as a power added efficiency of 38.6%. Here is a comparison of large signal performances of different technologies. So you see on the empty data points are load pool or pre-matched devices, whereas the field data points are MMICs. On the left side, yes, you have peak power added efficiency against frequency for different technologies, 2 different types of indium phosphide HBTs, silicon germanium HBTs, and gallium nitride HENTs. As you see, if you follow this state-of-the-art trajectory, indium phosphide gallium arsenide HBTs really stand out in G-band in terms of peak power added efficiency. Here we report the record G-band power added efficiency as 38.6% at 170 gigahertz. In this other figure here, we have only indium phosphide HBTs, gallium indium arsenide or gallium arsenide antimonide as base material, is PAE versus power density. As you can see, the result that both Sarah and I report are extremely competitive in terms of power efficiency versus power density. I'm just briefly going to conclude, as time is our enemy. We have measured load polling of our devices. We have examined different device layouts, examining the trade-off between the gain and power for different device dimensions, so different fingers. We've seen different configurations, common emitter and common base. We've seen that common base has a higher gain, but suffers from instability. By increasing the number of fingers, we managed to reach a 14.5 dBms power output, but there is a trade-off between gain and power. Then I've shown you different epitaxial layers. You've seen how by tweaking a little bit the emitter and the collector layers, we can achieve better thermal performances and thus better power properties with a record 38.6% PAE. Some limitations very briefly. The measurements are limited by the maximum input power that the extender can provide. Inserting an amplifier in the loop is not possible, as it will act as an isolator in the reading of the output. So this is really something that comes from the extender. Plus the PAD embedding. As a future work, we have to de-embed the pads, measure in higher bands, even though PIN is a problem in higher bands. And on our side, we look forward to realize multi-finger emitter fin DHBTs, which has possible power. This concludes my talk. Very sorry